Hello and welcome to this section of Calculus, Extra Practice with Integration. In this section we're going to figure out how to calculate the surface area of a three-dimensional object that's rotated about the x-axis. So notice before what we've done with the disk method and the washer method is we had a function, we rotated about the x-axis and we're calculating the volume of that object. And then we moved on to the shell method and we said, okay, we can take functions and we can revolve them around the y-axis and use this slightly different method to get the volume. But in all cases, what we've been doing so far is figuring out how much space something occupies. It's the volume, right? But we all know that calculating the surface area of three-dimensional objects is also very useful, right? And so you can use calculus to calculate the surface area of three-dimensional shapes, much like we were using it previously to calculate the volume. So to show you what I'm talking about, just to kind of make sure you're on the same page with me, if I have, some xy plane here, now let's call it x and f of x, I might have defined some kind of shape here that I'm calling f of x, right? And then I might revolve this guy about the x-axis. So as we have already done many times before, that is going to yield, just to make it a little bit easier to manage, let me go ahead and draw this guy just a little bit closer to the axis like this. What this is going to yield is basically a mirror image, something like this. And so you get a shape that would kind of look like a vase, let's say, for a shape like this. Of course, f of x could be any shape you want. We already know we can use the disk method to calculate the volume of this object by integrating from a to b. But what we want to know is how to calculate that surface area. In other words, if I had to buy paint to paint the outside of the object, how many square centimeters of paint coverage would I need that to have? That's what surface area is, right? So let me just write down, what the answer to this guy is. What we're going to do is let f of x be non-negative, which means a positive function above the x-axis. A non-negative function, and differentiable means we can take derivatives of it on some interval a, b. The reason we have a, b here is because this first part of the curve we're calling a, and we're going to end up integrating to b. This is the same thing that we're always doing. Then the surface area, SA, I'm going to call the surface area, is going to be the integral, you might guess, from a to b, of 2 times pi times f of x times the square root of 1 plus, now watch carefully what's inside of here, f prime of x, close the bracket, square it, all this is under the square root, dx. Okay, now if you notice, when we talked about the disk method, and we talked about the washer method, and even when we talked about the shell method, I went through great lengths drawing a picture and showing you how those relations, how those integrals actually do calculate the volume of your object when we were doing that before. You can do a similar thing to derive this kind of integral. But what ends up happening is it's not quite as obvious to draw a quick picture and show you how this happens. So if I were going to prove this to you, I'd have to break it out and I'd have to divide the drawing up into these little quadrants and I'd have to make a lot of assumptions and draw a lot of intermediate equations, and eventually it would condense down into this. And it's not quite as straightforward as it is for shell method and disk method and washer method. So those are kind of easier to understand, basically, what we were doing before. It's not hard or impossible for you to understand where this comes from, but I have to make judgment calls sometimes, and my judgment call this time is that it's going to be